So we're already familiar with the idea of coordination compounds in some sense because we covered complex ion formation. And what a coordination compound is an ionic compound, so cation, anion, right? That consists where at least one of the constituents is a complex ion. So when we were talking about things like cobalt, for example, CONH3 4 2 plus as a complex ion, that would be paired with something like chloride as a compound. So this is the complex ion that we were dealing with in previous chapters. And this is the counter ion that makes up the charge so that the whole thing overall is neutral. So a coordination compound has at least one complex ion, and it can have two as well. Now, I'm not going to spend a lot of time going over Vesper theory, but really quickly, right, if you have an atom in the middle and two electron groups, and we usually go like this, right? This is the sort of the standard Vesper notation where you have a central atom A, and then you have groups, atoms on the outside, those will be X's. Something like that has to be linear because in Vesper theory, these two groups have electrons around them that repel each other, and the lowest energy configuration is to have them split apart. We also talk about hybridization and stuff when we do this, but we're not going to do that in this chapter, but just the idea of these two being on opposite sides to get them farther apart. If you have three groups, then what happens is they'll take on a configuration perhaps like this to get the groups to be further apart. Now this angle's 180, this angle's 120, and this is trigonal planar. Now, when we look at four groups, we could have AX4. We'll have four groups. We usually draw it like this. And this is tetrahedral. Now, you can also draw it like this. This is a perspective drawing where I put the atom in the middle. These two bonds that I drew in black are in the plane. And then you have one that comes out and one that goes back. And these would be what gives the diagram perspective. So I have an X in the back and an X in the front, which I'll make bigger because it's in the front. You don't have to make it bigger, but that's normally just makes it a little easier to see. Normally they're all the same size. So this is a tetrahedral arrangement of groupings. And then what happens is you go beyond four groups. Now, if you remember, you can have lone pairs. So if you have one lone pair, this is trigonal pyramid, if you're trying to pull this out of your head. If you have two lone pairs, then you're going to be bent. All right, so these you can also have for trigonal planar, you can have one lone pair, and this is known as molecular geometry. It would serve you well to sort of review those because they will come up on your final exam. Now, once you get beyond the four basic groups, which probably got reinforced a lot, then we can go to 5 groups and 6 groups. So with 5 groups, there's a couple of possibilities, but we typically can draw it like this, A in the middle, and then I'm going to give this a perspective drawing format. And then I have one going back and then one coming forward like this, okay? So these three bonds, these three bonds are in the same plane. This one goes back, this one goes forward. This is called a trigonal bipyramid because it's a, if you think about pyramids, right, well then you have four corners, right, at the bottom, but a trigonal pyramid has three corners at the bottom. Not right corners, obviously, but three corners at the bottom. It has bond angles of 120 and 90 at the same time. And if you're missing a group, it'll happen at the equatorial atoms. And not the axial. And energetically, it's more favorable to remove equatorial. That is, you can get the groups further away from each other, in essence, in general, because these 90-degree interactions are kind of expensive as far as energy goes. So like this is a 90 degree, this is a 90 degree, and then between this X and this X, that's also 90, and it's reflected at the bottom, the same kind of interactions. So by pulling one of these off, you get rid of those 90-degree interactions and you stabilize it. And the last and the other important one for this particular set of lectures is octahedral, which is shown, but I'm going to go ahead and draw it in AX notation. Okay. So we usually have a central axis, and then we send two of them back, and then two forward. And like you can see in the diagram to the left of what I'm drawing, right, you can also draw it like an octahedron. That is, actually draw the octahedron, show the bonds in between, but actually sketch the shape on the outside to help give it perspective. I won't be doing that, but that's just the idea. Now, one of the things that happens is if you take off two groups, you take off one from the axial on this one, and one from directly opposite. So the lone pairs that are left are on opposite ends. That's what gives us what's called a square pyramid or square planar arrangement of the groups. You'll have you'll have a square, and what we're looking down at is an open orbital on this end, and then if you flip it over, there's one on the other side as well. So there's four geometries that really happen that we're going to be talking about. Well, actually, we're only going to be talking about two of these geometries for the most part, but there's several different geometries that are possible with transition metals. In particular, we're going to be looking at square planar and octahedral. Maybe we'll have a little tetrahedral or a trigonal bipyramid in there. I can't actually recall at this point. But anyways, these are the primary complex ions that we'll be looking at. Now, one of the things that happens in complex ions is actually it's a free metal ion. So unlike when you did these structures in Chem 1A, unlike when we did those structures in Chem 1A, in a coordination compound or complex ion, what's happening is a group is coming from the side, and this is known as the ligand. That's why it's called L in these diagrams. And unlike the covalent bonding that we were talking about in Chem 1A, where one electron comes from each group, what actually happens in the ligand is both electrons come from the ligand, and it forms a coordination bond. So let me get to that on the next slide. So these ligands are what we call Lewis bases. If you don't remember that definition, hopefully you do. But a Lewis base donates electrons. And because it's donating the electrons, then the metal ion, right? So let's say it's cobalt 2+, is a Lewis acid. And it accepts electrons. So both electrons come from the ligand, and then I guess one of the things they have to have is lone pair electrons on them. Some examples of ligands are like the chloro ligand or hydroxo ligand. There's also amine, methylamine. Ligands typically are negatively charged or neutral, because positively charged would be repelled by the cobalt charge, right? and then have these free electrons. We end, if they're anionic ligands, that is, they're a negative charge, we end them with an O, just so you know. Right? Now, there are in general two kinds of ligands, and these are known as monodentate and polydentate. Now, you can break the polydentates down into more kinds, like a bidentate. So this is ethylenediamine. Now, ethylene means two carbons, and an amine group is this NH2 group. So it's got two amine groups, so we call it diamine. So ethylene diamine, one of the common ones. Now, chloro and hydroxo, right, only have lone pairs on one atom, and so they can only serve to be ligands in a coordination compound, typically with one cation. Amine only has one lone pair for sure, can only coordinate with one, right? But ethylenediamine has two lone pairs on it, which are far enough apart, basically 5 and 6 atoms apart, four or five atoms apart for the lone pairs is kind of like the range that we're looking at. And then what'll happen is they'll coordinate with an atom to sort of make a 5-membered ring. Okay, I'll talk about that too in a second. But this is known as a bidentate ligand. It falls in the category of polydentate. Now, the term dentate, just so you know, comes from teeth, like your dentures. So when you're first born, you don't have teeth, so you're not dentate, right? But then all of a sudden you grow one tooth, and so you're a monodentate ligand. And then eventually you get more teeth, top and bottom, and you become bidentate. And then right now, hopefully, you're probably polydentate, so you got a lot of teeth in your mouth. And then you get older, it goes backwards. Anyways, ethylenediamine can form these 5-membered ring-like structures. So here's the metal atom in the middle, and the ligand attaches. Now this is just a free metal ion, and it has d orbitals and no other things attached to it. And so in order to make a bond, it has to make a bond through a lone pair. Now the lone pairs like this, there's 1, 2, 3, 4, 5. That's typical of the span that you need, 4 atoms plus the 5th, which is the metal ion, to make the link, the polydentate link on this. Now, if you think about the shape of this, it almost looks like it's like this weird trifold shape. Okay, we'll talk about that when we talk about stereochemistry later. But you can fit in an octahedral complex, you can actually fit 3 of these polydentate ligands onto the surface or onto the outside of the central atom. There are other very common polydentate ligands. Ethylenediamine tetraacetic acid. I typed it out because I didn't want to trust myself. But if you type this in, I'm pretty sure it's in the Word dictionary. So you can, if you want to check the spelling, you can type it in. It's a hexadentate, so it has 6 teeth, right? So this one's a real big boy. And you'll notice what happens. It's oh, I just noticed a mistake in this formula. That's a 2. It's got, this was a copy and paste error. It's got acid groups on the ends, carboxylic acid groups, and so depending on the pH, these are either protonated or unprotonated. So there are 4 different acid groups, so think about 4 different pKa's. So depending on the pH, it determines the degree to which these are free to be able to bond. So EDTA, though, as a hexadentate ligand, can make 6 attachments to the metal ion. In this case, they put lead in the middle, right? And this is an extremely stable complex ion. It has these generally have really high formation constants. So if you remember, right, coordination compounds have really large equilibrium constants. And at the time, I just sort of brushed it off and went past it, just said they're really big. The question now comes up, why is the equilibrium constant so large? And I could have really covered it in the thermodynamics chapter, but decided this is probably a better place for it. It wasn't super important at the time. So imagine that you have this coordination compound, right? And you bring ethylenediamine up to it. Now, this is what the structure ends up looking like. Well, in the process, where these are all aqueous, in the process, the ethylenediamine will release 6 ammonia molecules in the process, right? So notice what happens to the entropy. Delta S is going to be positive because you went from having 4 now to having 7. Now, when you do this to a free ion in solution, one of the things people forget is cobalt is actually never really free in the solvent because water is also a ligand. And so there are actually many what we call spheres of hydration or waters of hydration that surround any free ion, even in an aqueous solution. So what ends up happening is when the ethylenediamine bonds to the cobalt, it keeps those waters of hydration from attaching as easily, and it frees up a lot of water molecules in the process. So it turns out delta S for these is very large, positive values, and delta H turns out to be small because you're not really gaining or losing any bonds, right? You're going to have the same number of bonds, but you're going to have released a bunch of ligands. So these polydentate ligands, like EDTA, for example, this guy, right, are really good at extracting metal ions like lead from your body. In fact, they're so good you have to be a little bit careful when you use them. But when somebody gets heavy metal poisoning, many of the treatments are based on ligands similar to EDTA in that they are polydentate ligands which can bind the free metal ions, or actually they could actually extract metal ions. So that's what you got to be careful of, that they don't start pulling other metal ions out of your body. But they can pull any of the free metal ions out of your bloodstream, and then your body can process them, or they can be filtered out. Okay, so delta S is large and positive. We're moving waters of hydration. So what that does, and because delta H is small, because you have the same number of coordination bonds before and after the reaction, you end up getting a relatively large negative delta G, which means K equilibrium constants will be large.